Eigenvalues and Eigenvectors. Let A be a square matrix of order n cross n. It has elements Aij. We wanted to introduce the concept of eigenvalues and eigenvectors. Let alpha be a scalar, which may be a real number or a complex number, and x is a column vector which has entries x1, x2, xn, and which is a non-zero vector. This alpha and x, they can be called as an eigenpair of matrix A, where alpha is an eigenvalue of A and x is an eigenvector of A corresponding to the value alpha, which is an eigenvalue. If Ax equals to alpha x for x not equals to 0. The non-zero clause of x is extremely important, because if x is equals to 0, then the things becomes very trivial and it's like 0 equals to 0. And we are interested in the non-trivial cases. Now we need to focus how to determine these values alpha and x. So we can begin with our original equation Ax equals to alpha x, and we can rewrite this as Ax minus alpha x equals to 0, and further it can be written as A minus alpha I into x equals to 0, which is a homogeneous system of linear equations where the variables are x1, x2, xn. Since we have already claimed x is not equal to 0, so to get a non-trivial solution of this homogeneous system of linear equation, the determinant of A minus alpha I has to be 0. And the determinant of A minus alpha I is actually f of alpha, and it is called as characteristic polynomial. And if we write this thing in a form of an equation, then it is called f of alpha equals to 0, which is characteristic equation. By solving this characteristic equation, we can have the values of alpha, and it will determine the eigenvalues of a given matrix. So here it was the way to actually introduce about the eigenvalues and corresponding eigenvectors. So throughout this lecture, alpha is going to be an eigenvalue and capital X is going to be the eigenvector corresponding to alpha. So now we'll begin with an example where we are going to learn how to actually evaluate the values of alpha and x. So let's begin with a 2 cross 2 matrix which has entries 1, 2, 0, minus 1. And we are looking for the values of alpha for this matrix, that means the eigenvalues. So let's solve this determinant A minus alpha equals to 0, which is nothing but the characteristic equation, which turns out to be 1 minus alpha, 2, 0, minus 1 minus alpha equals to 0. And once you solve this determinant, it is going to turn into 1 minus alpha into 1 plus alpha equals to 0, which is essentially gives the values of alpha as 1 and minus 1. So these 1 and minus 1 are actually the eigenvalues of the given 2 cross 2 matrix A. Now let's determine the corresponding eigenvectors. So we'll start with the alpha equals to 1, and again we'll take the equation Ax equals to alpha x, and we are putting the values of alpha here as 1, so it turns out to be A minus I into x equals to 0, which is actually 0, 2, 0, minus 2 times x1, x2 equals to 0, which is a homogeneous system of linear equation and which is quite trivial, and it provides the value of x2 as 0 and x1 may be any real or complex number depending on the given field. So for the eigenvalue alpha equals to 1, the corresponding eigenvector is c comma 0. So the examples could be 1, 0, 2, 0, 3, 0 are the eigenvectors. Let's do the same thing for alpha equals to minus 1. So the corresponding CH equation will be A plus I x equals to 0. And once we solve it, 2, 2, 0, 0, x1, x2 equals to 0, 0, which is again a quite easy system of linear equation. and it turns out to be x1 equals to 0 and x2 equals to some value d, which may be a real number or a complex number. So the corresponding to eigenvalue alpha equals to -1, we got the eigenvector 0 and d as a vector where d is any real or complex number. So examples could be 0, 1, 0, 2, 0, 3, in general 0, d, and obviously d has to be non-zero. Same for the C. Now let's take a example of a higher order matrix. This time we are having a 3 cross 3 matrix which are having these entries. -2, 2, -1, 2, 1, -2, -3, -6 and 0. So if we put this equation into our eigenvalue equation, so it is going to give us the characteristic equation a minus alpha I equals to 0, and this means the determinant -2 minus alpha 2 -3 2 1 -6, sorry 1 minus alpha -6 -1 -2 0 minus alpha equals to 0. It's a 3 cross 3 determinant. So if we expand this determinant, so it is going to be alpha cube minus alpha square minus 221 alpha minus 45 equals to 0, which is actually our characteristic equation of this given matrix. It's a cubic equation and we can factorize it and we can have the roots of this equation, and once you factorize it, it is coming out to be alpha minus 5 into alpha plus 3 whole square equals to 0. So from here we are quite clear that the roots of this CH equation are alpha equals to 5 and -3 2 times. So these are the eigenvalues of this given matrix A, which are 5 -3. Now let's determine the value of eigenvector corresponding to each of them. So let's begin with alpha equals to 5. And let us put this into our eigenvalue equation. A minus 5i times x equals to 0. So let us put the value of a here, and once we'll put the value of a and solve this matrix A minus 5i, so it is going to have the entries -7 2 -1 2 -4 -2 -3 -6 and -5 times x1 x2 x3. So here we had a 3 cross 3 order matrix, so the eigenvectors will take this kind of shape which has 3 tuples. Since again it's a homogeneous system of linear equation, to solve this system, let's convert this coefficient matrix A minus 5i into row reduced echelon form. So let's write this matrix once again and try to convert this matrix into row reduced echelon form using the suitable row operations. So I'm keeping the first row as it is, -7 2 -3, and now we'll use the fundamental row operation first in row 3 followed by into the row 2. So R3 is going to be replaced by R2 plus 2 times R3, and this is going to change third row into 0 minus 8 and minus 24. Sorry, it's minus 16. And now this we'll use the row operation for the second row. It is 2R1 plus 7 times R2, and it is going to change the second row into 0 minus 24 minus 48. Now we see the third row and the second row are the scalar multiple of each other, so we can apply one more fundamental row operation in the row 2 followed by row 3 followed by row 2, and it will turn the matrix into 7 minus 7 2 minus 3 0 1 2 0 0 0, which is actually in the row reduced echelon form. And now further we'll put this reduced matrix into the equation form times x1 x2 x3 equals to 0, which is a 3 tuple. So if we write in terms of equations, so we are going to get minus 7 times x1 plus 2 times x2 minus 3 times x3 equals to 0. And another equation is x2 plus 2x3 equals to 0. So it is a system of linear equation which got 3 variables and 2 equations. So one of the variable is going to be an independent variable. It could be any one, either x1 x2 x3. So we are choosing for x3 a random number, independent value, say a. So by the choice of x3 as a, we can have the value of x2, which is going to be minus 2a, and the value of x1 we can determine by putting the values of x2 and x3 in equation 1, and it is going to have the value of x1 as x1 equals to a. So we got the solution of this system of linear equation, and that solution is in a form of a vector. It is a minus 2a and a. So this is the class of eigenvectors. If I take a out of this, so it is going to have the value 1 minus 2 and 1. So any non-zero scalar multiple of 1 minus 2 1 is going to be an eigenvector of this matrix for the eigenvalue alpha equals to 5. Let's do the same thing for the another eigenvalue which is repeated, alpha equals to minus 3. So let's put this into the eigen equation. So a plus 3i into x equals to 0. Let's put the value of a here, and we can again have the homogeneous system of linear equations, and it is going to be 1 2 minus 3 2 4 minus 6 followed by minus 1 minus 2 and 3 times x1 x2 x3 equals to 0 0 0. So again we collected our coefficient matrix and we are going to convert it into row reduced echelon form, which is quite easy in this time. And we got the equivalent form of row reduced echelon form of initial matrix. And when we convert this into again system of linear equations, so it is going to be only one equation, x1 plus 2x2 minus 3x3 equals to 0. Again it's a one equation and three variables, so two of them are going to be independent, so I'm choosing independent values of x3 and x2. And we can have the value of x1 in terms of x2 and x3, which is minus 2d plus 3c. And let's collect them together and put it into a form of a vector. So x1, x2 and x3, it is going to be minus 2d plus 3c, d and c. What we'll do, we'll split this vector into two independent vectors by separating the c and d. So it can be splitted like this: c times 3, 0, 1 plus d times minus 2, 1 and 0. So these are two linearly independent solutions of this system of linear equation, and for the eigenvalue alpha equals to minus 3, we have two linearly independent eigenvectors, and these eigenvectors are 3, 0, 1 and minus 2, 1, 0, or their scalar multiples.